we're going to be looking at the power board, which is one of the components that we use for our digital readout solution. This can be used to communicate with a variety of RS485 devices, for example, remote I/O ports or variable frequency drives. Another important feature of this board is that it provides a clean and safe power supply for the Raspberry Pi. This is an important aspect for anything besides hobby or lab testing purposes. The normal power supply that comes with the Raspberry Pi is a USB type, but the problem I have with those is that regardless of the connector that you have in your Raspberry Pi, it's not a very secure attachment way. It's easy to get it disconnected and the connectors can rust, they can stop providing you a clean connection. With this Power Hat, what we get is we have screw connectors, which will provide you a more secure way of connecting your board. And then it will also make sure that you have plenty of power to power not only the Raspberry Pi, but also any external accessories that the Raspberry Pi might be using itself. Let's take a look at the wiring diagram, and I'll show you some of the features on this board. Of course, everything is open source. You can download these models, you can get them from the store. We're going to be providing the links at the end of the video, and you'll be able to find them if you're interested in one of these guys. This is the repository that you can find on GitHub. You can clone this locally on your machine, and you will find that it has the KiCad project in here, including a schematic and also the PCB layout. There is also a production folder in here which contains the Gerbers and the files that can be used, for example, if you want to order this on a manufacturer such as JLC PCB. So I already have this repository cloned on my machine, and I'm going to go directly on KiCad where I have my project open already. And then down here you'll see all the files. You have the PCB here and you have your schematic as well. So we're going to be opening the schematic first. So what you see here, this is a representation of the connector that goes over to the Raspberry Pi. Here you will see that there are a few ports that are connected, including the power supplies. So what we do is we feed in this 5 volts here. This is the power that we are providing to the Raspberry Pi using our board. And then we are consuming the 3.3 volts that the Raspberry Pi would generate for us to power some of the local devices that we have in here that handle the RS485 communication. These 2 ports here, the transmit and receive, are going to the UART0. This is your communication with the RS485 interface that we provide in this board. And then there is an optional output, which is an extra feature that was added in the last version of this board, which is a user LED. This can be used to signal statuses, communicate alarms or errors, or just not be used at all if you don't need it. Let's go over here to the right where we have some of the more interesting parts. The top section here is the power regulation and filtering. It should provide some basic protection and some of the fundamentals that will ensure that we're not going to blow out our Raspberry Pi, as well as making sure that we can handle a variety of power supplies. So what you see here on the left of this block is the AC or DC power input, and then we have a fuse, which is now for 2 amps. Then there is an ESD protection diode, which is pretty capable and big unit, so that we can ensure that if we are feeding some unwanted power over here, we can trip the fuse and drop all the power through this ESD protection rather than damaging all of our other components. And after that we have a bridge rectifier. This is an SMD component which has a decent amount of power capabilities, and this will take care of either giving you the right polarity if you're using DC, so you don't have to worry about how you connect this on a DC power supply, or if you're using an old school transformer to give some power to your Raspberry Pi, then we're going to actually rectify that from AC to DC. Here on the right, it's an LM2596. It's a switching power regulator. It has its own filtering capacitor at the input, and it has its own filtering capacitor at the output, and a 47 micro Henry coil. Now, coils might change, and usually what you want to do is you want to choose a coil that is tuned for proper operation based on your source power supply. And knowing that most people will probably have laying around 12 volts power supplies from other applications with 1 or 2 amps of capacity, that's where we optimize the selection of this value. So the 2596 here is going to be working at its best optimal conditions when the power supply is around 12 volts. The 2596 works fine up to 40 volts. That's a safe value to use, and that's why I selected this SMDJ40CA. This value is suitable for the absolute maximum ratings that the LM2596 requires. That means that if you have, for example, a 24 volt transformer, like one of those old school transformers that are used for doorbells, for example, you could use one of those, just hook it up here, and with your basic circuit protection and the rectifier, you would be able to use that as your power source for the Raspberry Pi. It's an interesting application because it might be something you have laying around, or it might be something that you already are using for another project or home automation system, and that might become in handy. So that's the reasoning behind having a rectifier in here. It's also making it easier for you to plug it in. You cannot blow this up by reversing your power supply. It doesn't really matter how you connect your DC if that's what you're using, because this rectifier will always provide the proper polarity over to the 2596. And it also opens the door for us to use an AC source if we decide to do so. This is the RS485 interface. We're using one of the many compatible SMD chips that allow us to convert an RS232 UART signal over to an RS485 signal. What we have here on the left side is a very simple transistor-based circuit which will control your transmit-receive signal. Of course, there's a small filtering cap which is just put as a buffer for this chip. Just a simple cap that goes together with a 485 interface chip, and then a small circuit that controls the transmit-receive signal, which comes from the Raspberry Pi. And then, hooked up directly to it, we have the receive and transmit signals. As you can see here in the output, there is no biasing resistors, there is no termination resistor provided in this circuit right now. But nonetheless, this chip comes with fairly decent ESD protection already out of the box. I think it's probably 4000 kilovolts. Worth probably checking on the datasheet if you have some noisy or danger environment where you want to use this, because you may want to have some extra protection on the output. But in the application and use cases we are envisioning for this, that's totally acceptable. Going down, we can see some more details about our messaging and communication LEDs on the board. A very simple LED that will provide us an indication that we got the 3.3 volts coming back from the Raspberry Pi. You have the user message LED, which is going to signal to us that whatever signal you send out from the software, you can turn it on and off if you decide to do so. And then the last one here is the transmit activity LED. So these are all the LEDs you have, and they should be pretty much enough to tell if your board is working fine, if you got a clean power supply coming to your Raspberry Pi, and also to tell you and signal custom messages or transmit status on your RS232 bus. Let me go over to the PCB editor so we can take a quick look at this as well. Definitely not a clean layout yet. It does what it's supposed to, and I think track sizing and dimensions are reasonably sized. There's plenty of room on the board where we can add more features in the future. Now what you see here is the drilling hole pattern, so this will match any kind of Raspberry Pi compatible hat size, dimensions, and drill pattern. This is your Raspberry Pi header. And then we're taking from the Raspberry Pi the 3.3 volts that is used to power the RS485 interface, as well as signaling to us that, yep, we indeed have a Raspberry Pi connected. And if you try to power on this board and you don't have a Raspberry Pi connected to it, this LED will be off. You'll not see nothing in here. This is going to stay off, and all the other LEDs will be off as well. So you might be thinking, well, maybe this board is not working, but that wouldn't be accurate, because in order to see this guy's working, well, the user LED, you need to program yourself. The transmit will turn on if you're sending data out with your UART interface, and the 3.3 volts is going to be on only in the case of a Raspberry Pi connected and not defective over to the board, because that's coming back from the Raspberry Pi. We're not generating our own 3.3 volts. It's questionable whether this is a good choice or not, but the main consideration I did when I implemented it this way is just making it sure it's simple and cost effective. And because we have only a single chip and an LED, we're talking about a few milliamps here. And the Raspberry Pi should be capable of providing plenty of power through the 3.3 volts line that we have going to it. So that's kind of, maybe answering some of the questions you might have about why this is done this way. Now let's go over to the input. So we have two connections in here. They are clearly labeled, so it should be easy to identify them and know where the connections have to go. The top one here is your AC or DC input. We have an inline fuse, which is the one you've seen on the wiring diagram before. This is our ESD protection diode. And then here's our bridge rectifier, which then goes into a buffering capacitor for the 2596, which is mounted down here with plenty of vias to make sure that we have all the necessary heat sinking so we can supply reasonable power without having to worry about overheating. Here's our coil. And then down here we got our buffering cap for the output. This is kind of the overview of our PCB. I'm going to switch over to a 3D view. So that's pretty much it from the hardware point of view. Please take a look at the repo. Leave us comments and let us know what you think about it. If you have any suggestions for improvements or future changes or features you may want to see on this to further improve the capabilities and features of this board. But for now, I just want to show you how this works and the checks you can perform on the board once you have it assembled and you have received it at home. This is an older version. There was a mistake with the drill holes, so it's been modified. We have two wires. They are the power input. So the first check I'm going to be doing now, I'm going to set it for 12 volts. I'm going to measure by the cap. That's the easiest place for me to verify right now. So let's put the terminals right there. And as you can see here, you have 4.96 volts, which is perfectly fine. We're gonna plug this into the Raspberry Pi. So we'll take the header and just carefully push it down all the way. I of course have soldered this out of camera. So now it should not boot, nothing should happen, but we should see that our 3.3 volts is working. So I'll turn on the power supply, and as you can see now we got all the LEDs turning on. That might be because of the status in which the Raspberry Pi is right now. Again, there's no operating system, nothing is running on it. But that's our confirmation, that's what we're looking for. What we want to see is that this LED turns on, and when we go in and measure what power is actually going out, there is a little bit of drop. As you can see, we're at 4.94 right now. We're using about 60 milliamps for the 12 volts power rail. So this is how the power board should appear on a unpopulated or a Raspberry Pi without operating system or anything running into it. One more test I'm going to do before we turn this off is I want to show you the advantage of having this bridge rectifier even when you're using DC. So I'm going to turn off the power here. We're going to be swapping the power leads coming onto the Raspberry Pi. So we'll reverse the polarity. And as you can see, there is no polarity marked on the input screws, and that's intentional because it doesn't really matter which polarity you actually use. It's always going to work fine as long as you have the right power supply applied to it, which is greater than 7 volts and smaller than 40. We can go in and measure, and this is indeed our 11.5 whatever volts we had from before with the polarity inverted, but thanks to the bridge rectifier, whatever goes to the power regulator always has the same polarity, and it's always going to work. So next step, we'll get a operating system installed on this memory card. See you in a bit, and we'll be taking it from there. Looking at the repositories from my user, in this list you will find all the projects that are part of the offering that goes together with the power board and the rotary controller. This OSPI repository contains a Raspbian-based distribution, which we are pre-packaging so that it has all the requirements and all the basics that are needed in order to use the RS485 communication. And it also includes all the libraries that are required in order to use Kivy for the rotary controller, which is a separate project we're going to be looking at in the future. To download the latest image that is built automatically whenever I make changes to this repo, you go to the homepage of the OSPI project and you look at the tags, you will see that there is a bookworm and it already has everything we need. So I'm going to go with this one. Click on this guy where we get taken to the releases page. And you can see here there are two versions. There is a light version, which does not include the modifications that I have made to the operating system to enable UART, for example, or the Kivy dependencies. It's about 700 megabytes, and then you have the base one, which includes all these other basic features that we need to use. So I'm gonna go ahead and download this guy on my computer, take a minute or so. Once we get this downloaded, at least for myself, since I'm on Linux, I'm going to be using DD to copy this image over to a fresh SD card. If you're on Windows, you can use Win32 Disk Imager or Balena Etcher. There's a long list of products that I think you can use here, as long as it's capable of writing the image in the format that it is here on the web page onto the memory card, then that's all we need. Right now we got the file downloaded, so I'm going to go ahead and open a terminal. Let's go to the downloads folder. You can do the same thing from Windows. You can use right-click button and unzip. So we'll do an unzip, and we're going to paste in here the name of the file that we just downloaded. And let's go ahead and inflate this. As you can see, we're decompressing the image. We're getting this IMG file, and that's the one we want. I'm going to actually use now a proper SD card from SanDisk, the Extreme Pro. Perfect. I'm going to plug in the new memory card. So just to double check, let's list our blocks again. As you can see, this is now a 64 gigabyte device. We're going to be writing to this instead. So we'll run the same command as before. So it's going to be again sudo input file is going to be the name of our file, which is the one we took from the zip file. The output file is going to be the memory card that we just plugged in. So it's still dev.sdb, and then the same flags as before. So let's go ahead and issue this command. A few more seconds, and we should be good to go. And we will do the same check. So we'll eject the disks and unmount them. And once that is done, we are going to mount them again and make sure that both file systems are visible. So now we are done with the writing. We will do it eject again. Of course, it needs to be done with sudo. So now my volumes are removed. I'm going to unplug my memory card. Let's go back to our file system. There's nothing listed in here. I'll plug in the memory card again onto my USB reader, and this time, if we're lucky, and we are, the file system is readable, and there's like a very quick confirmation and check that you're not going to be trying to plug in something broken onto your Raspberry Pi. So now that we have confirmation that everything is looking good, I'm going to be unplugging my memory card again, and I'm going to be plugging this memory card onto the Raspberry Pi. The example I'm going to give you guys now is about connecting the RS485 port of our Raspberry Pi Power Hat with an RS485 device. What you see new in this picture is the WellPro module. This is a cheap Chinese RS485 device that can be used to read inputs, digital inputs, and to send out digital outputs. And it also has some analog inputs that we might be experimenting with. I already set up all the connections, so right now I'm powering this I/O board with the same power supply that is being used for the Raspberry Pi, and then I connected the A and B channels for the RS485 communication. So everything is already configured, and I conveniently placed a label on the serial port on the expander here, so we know that we have address 3 and we have the connection speed is 38,400 and it's 8N1. So these are pretty default values. A lot of common devices have 9600 as the default speed, but I brought this one up to the maximum. You can set this guy up for your purposes. So again, these two cables are going to the RS485. They're short, so we don't really have any concerns about termination, or even with this speed, I don't think it's going to be a problem. And then here we have the power coming in. This is the status LED. I don't know if it's visible on the camera, but this guy is powered. It's already working, and we're going to be changing these values, and we're going to be seeing how this guy works when it's connected with an RS485 interface, such as the one that we have on the power board. So I'm going to move over to the computer. I'm going to start the screen share, and I'll give you a quick tour of these 10 lines of code that I just quickly put together, so we can get a feeling about how communication works and how easy it is to set it up with the OSPI image and with this RS485 interface. We're back at the computer now. I have PyCharm open, so we are connected to the Raspberry Pi. You can tell it by the settings I have here on the bottom. Again, I'm logging in using my key, and I'm using the root user. and I already have set up my remote Python interpreter. So anything we run here will be actually executed on the Raspberry Pi. So what I have here is a very, very simple example of what can be done, for example, with Python if you want to use a RS485 device using Modbus. There is this beautiful library which uses, I think it's purely Python, but this is minimal Modbus. It's a library that allows us to communicate very conveniently with Modbus devices. And setting it up is very straightforward. The only thing we have to do is specify the port and address of our Modbus device. So our port is the usual one. We use dev serial 0, and slave address 3 is what I have arbitrarily assigned to my port expander. So you might have different values in your case. And then down here we have the Modbus speed. Well, that's the serial port speed, which is going to be 38,400 for me. And then I also set these two timeouts to be lower than the default. So if there is a failure, we will see it without having to wait for a long time. Very simple try-catch exception here. So if something fails, we can see what's going on. And then on the bottom, I just wrote a few lines that will write bits. Those specific values depends on the device you want to use. In our case, I can show you the documentation that I'm using for this specific type of input-output card. And here is a list of all the commands that are supported. So what we want to do here is we want to write a digital output. So we are going to have to follow the instructions in this paragraph. And as you can see here, we have a module address, which I have set to 3. In this example, they're giving you 1 as the example. And then we have a function code, which is write bits in our case. The address is 0, so that's where we start. And then we want to write the value for coil opens and closed based on this. This is following the Modbus standard. If you have to write your own protocol or use a different language, this is a good reference that tells you how to use that. And this final number here, again, this is part of the standard that Modbus provides. And that's essentially a checksum for the data we're going to be preparing. So it will depend on what data you send out. So with that said, let's now take a look and see how this code works. What we're going to be seeing is the LEDs from the digital outputs should turn on and off in sequence, and I put an interval of 0.1 seconds here so we can see the light going left to right. And that's exactly what we're supposed to see. So let me press play here and we can take a look at how this thing works. So as you can see, our LEDs are moving left to right and everything is working as expected. And that's pretty much all you can do with Modbus device. Of course, there is plenty of commands and plenty of different devices that you can control with Modbus. Very common use cases to read and write variable frequency drives, for example. You can change the parameters for those. You can control the speed. And they all use a similar approach. Instead of using bits, you might have to use bytes or words, but the complexity is not much different from what you're seeing here. You can also take a look at the rotary controller board, which uses a slightly improved version of this library. It uses a communication class to send and receive all the information about what's going on in the card and to read the position for the scales, for example, or change the parameters for the indexing. It is all fully implemented in Modbus as well, and having it with the power board like you see here, it's a very convenient approach that allows us to communicate not only with our rotary controller cards, but also with other devices at the same time, thanks to the benefits of having RS485 in the background. So that's pretty much all there is to say on the card. If you're interested, you will find the cards available starting from this week already on our webpage. So go take a look. And if you have any questions or comments, please let me know. And we'll be seeing you at the next video. Thank you very much.